In this section, we'll cover a few other elements of a well-designed experiment. In the previous section, we designed an experiment to determine if caffeine affects pulse rates, and we did this by comparing two groups of subjects. One got regular soda, the other got caffeine-free soda. We talked about why it was important to create groups that are as similar as possible, with the only exception being the treatment that they receive or don't receive. If there are other similarities between the groups, it could confound the results, and the one we discussed in the last section was the amount of sugar in soda, and that's why the control group gets caffeine-free soda. So they're similar to the treatment group with respect to the amount of sugar they're ingesting, and the only difference is whether or not they get caffeine. What we haven't discussed is how we decide which students receive that regular caffeinated soda and which ones receive the caffeine-free soda. If we let them decide themselves, it's possible that they'll create groups inadvertently where the students who drink more soda are going to choose the regular soda, and students who tend not to drink soda or don't drink caffeine typically will choose the caffeine-free soda. And this is introducing an additional variable that might affect pulse rates, namely caffeine tolerance. If we get to the end of this study and we see no effect, is it because caffeine doesn't actually have an effect on pulse rates, or is it because we're only giving caffeine to people who already have a high tolerance for it, and the people who have a low tolerance don't get caffeine at all? So when it comes to deciding who gets which treatment in any well-designed experiment, we want to assign experimental units to those treatments using a chance process. We call that random assignment. This is going to follow the same process that we discussed when we were covering sampling techniques a few sections back. If we have 20 students volunteering to participate in this experiment, how would we randomly assign them 10 students each using slips of paper? Well, we could write the letter A on 10 slips of paper and the letter B on the remaining 10 slips, shuffle them all up, have students draw out random slips of paper. Anyone receiving A would receive the soda with the caffeine, and anyone who's in group B would receive the soda without caffeine. Now, we're labeling them A and B instead of caffeine and placebo because we want these students to be blinded to which treatment they receive. Instead of assigning treatments to subjects, we also sometimes want to assign subjects to treatments. So in this example, we're going to explain how we would randomly assign 10 students to each treatment. So again, we have 20 volunteers. We're going to label the students from 1 to 20. We'll use a random number generator to generate 10 different integers from 1 to 20, ignoring repeats. Okay, if you write different, we really don't need to write ignoring repeats, but it's good to have it in there anyway. The students with these numbers will receive the soda with the caffeine, and the others will receive the soda without caffeine. By randomizing the assignment of treatments, it should distribute students who have a high caffeine tolerance into roughly the same numbers in each group. And for students with low caffeine tolerance, they'll also be distributed roughly equivalently across the treatment and control groups. So the purpose of randomly assigning treatments to subjects is to create two groups that are about the same with respect to every variable that might affect the response, not just caffeine tolerance, but really anything that may affect their pulse rates. One thing to keep in mind when we're assigning these treatments is we need to make sure we have enough subjects in order for the randomization to work and spread out those sources of variation. Let's say gender would affect the response variable in an experiment, and we only had 6 subjects. 4 of those 6 are female. If we were to split them into 3 groups, at least one of those groups would be entirely female. And that could cause a confounding variable in our results. So instead, if we had a larger sample size, 57 females, 37 males, again, it doesn't have to be equal. There just have to be enough of them where when we split them up, it creates a balance between them. So in this case, it would be almost impossible that one of these treatment groups would be entirely female if we're splitting up these 94 people into 2 groups. The idea that we have enough subjects to create these roughly equivalent groups is called replication. The last component of a well-designed experiment is something called control, where we're trying to minimize other sources of variability. So let's say in our experiment, we allowed students to drink as little or as much as they wanted. At the end of the experiment, we record their changes in pulse rates. They would be a lot more variable because some students have drank a lot more soda, they've ingested a lot more sugar, some ingest more caffeine than other ones. All right, so this increase in variability makes it more difficult to actually identify an increase caused specifically by caffeine. So we want to make sure that everyone drinks the same amount. The treatment group is getting no caffeine, the control group is getting no caffeine, the treatment group is getting a specific amount of caffeine. This is an example of controlling outside sources of variation by limiting the amount of soda that they drink. The author of the textbook actually did this experiment with his class, and we can see the difference. Soda intake controlled. So in this left graph, we can see these students all drank the same amount of soda. Those without caffeine are centered around 0 in the amount that their pulse rate changed. Those with caffeine increased about 5 or 6. All right, when they didn't control the amount of soda that they're drinking, both of those distributions are way more spread out. All right, and it's harder to spot a difference when the data is all spread out like this one. We can see in this graph on the left that this average pulse rate is definitely increasing when students consume caffeine.